So we're looking at whether a sequence diverges or converges. So the next big idea is what we call, I want to write B for big. I wanted to write D for divergence. Divergence. What's called the divergence theorem. Given the name, what do you think it tells us? Whether something diverges. Right? That's all it tells us. So it goes like this. If the limit of some sequence, an, as n goes big, so we look at the sequence over its terms, if it does not go to 0, then the sum of those terms, as I goes from 1 to infinity, of those a sub i's, that has to diverge. That's called the divergence theorem. There's a special version of this called the contrapositive. And contrapositive means to flip it and do the opposite of each. So if I flip it, that means I have to talk about the sum first. The opposite of diverging is converging. So the contrapositive is if the sum, and again, infinite sum of these ions, if that converges, then the individual pieces in there that we added up, that limit of the individual terms, had to go to 0. Okay, so notice the things we start with. If we have a sequence that doesn't go to 0, we know the sum must diverge. If we have a sum that definitely converges, then the terms had to go to 0. So I'm just going to give an example of the first part here. Take the limit as n goes to infinity of n plus 1 over n. Just think about what those terms look like. So this is just a sequence. It's not a sum. The first term is going to be, let's see, is that the one I want to look at? I want to look at the other version of it. I want to flip that. We could do it on that one too, but we looked at this limit before, both this one and the flip of it. Either way, it goes to 1. What do these look like? Well, the first term is going to be 1/2, second term is going to be 2/3, third term is going to be 3/4, and so on down the line. This sequence right here is increasing. And the values of it are always less than 1. So this is monotonic and it's bounded. Right? If it's monotonic and it's bounded, we know it has a limit. We also know the limit's 1 from our previous work. Now, each of these numbers here, since it's increasing, they're greater than the first term 1/2. So in general, n over n plus 1 is, oops, wrong direction, is greater than 1/2 for all n, or equal to, sorry, because the first one is equal to. Therefore, the sum of the left side is always bigger than or equal to the left side, especially because I'm letting n go from 1 to infinity. What do we get if we add up infinitely many 1/2s? Infinity. It still just grows forever. Yeah, so this right here diverges. It diverges specifically by increasing forever, without any limit. Often we say increases without bound. And it's the smaller of these two sums, right? So consequently, this thing right here also diverges. It's kind of getting squeezed up by the other one. So that's just one example. If you have an increasing sequence that reaches a ceiling, you can always find a point for which it's always bigger than some real number. And that means the sum must be bigger than adding that whole number up forever. And it's just always going to diverge. something important about the divergence theorem, so I just want to restate it again. Limit, if we know this does not go to zero, then that implies that the sum of those a sub n's diverges. The converse of that goes the other way. Sorry, not the converse, the contrapositive, which is a converse and an inverse together. If we know the sum converges, then we also know that the limit of the individual pieces we're adding have to go to zero. Question. What about knowing that the limit of the pieces we're adding does go to zero? Do either of these theorems start with the sequences go to zero?
Like starting from zero?
The sequences go to zero. So for example, the limit as n increases forever of 1 over n goes to zero. The limit as n goes to infinity of 1 over n squared goes to zero. The limit as n goes to infinity of 1 over the square root of n goes to zero. Each of these theorems, right, this first one up here is called the divergence theorem. The second one is just the contrapositive of the divergence theorem, which contrapositive means flip it and negate it, change the order of the premise and the conclusion. Do either one of these start with that condition right there? No. Therefore, if you know the limit of the terms goes to zero, you really don't know anything about convergence of the sum. You're left in this intermediate place like, oh, it doesn't fit the divergence theorem, but it also doesn't, I don't have any theorem that talks about convergence here. So a series for which the sequence of values we're adding goes to zero just means we have a candidate for convergence. Otherwise, if it didn't go to zero, it definitely diverges and we're done looking at it. Okay, so that's the nice thing about the divergence theorem. You just check the limit of the terms. If they don't go to zero, boom, done. No more looking at the sum because the sum has to diverge. Okay. So now we need to deal with, okay, if the limit does go to zero, now we got to do more work to figure out what's going on. All right, so next, more work. The next big idea in determinant convergence is called the integral test. And we've kind of played around with this idea already, and it goes like this. We're going to let some function match the terms we're trying to add up. And we're only going to do this for functions f of x that are continuous. So f of x, is continuous, positive, and decreasing. So just think about that for a second. I have some function, the terms are always positive. So maybe for n or x equals 1, I have that point right there. It's always positive and it's decreasing, so that means the function must do something like this. It must asymptotically approach the x-axis. The x-axis is y equals 0. So in other words, part of what I'm saying here in this condition is that the limit as x goes to infinity of f of x is equal to 0. F of x is continuous. F of x is always greater than 0. Right, so those are my conditions. So if I have some sequence and the function version of that matches these three conditions, continuous, positive, and decreasing, then what I can say is the sum of those a sub n's as n goes from 1 to infinity, and the integral as x goes from 1 to infinity of f of x dx either both converge or both diverge. And at this point in our careers, we are better with integrals than we are with sums. We're just scratching the surface on what we can do with sums. So we're going to use integrals to help us figure out whether sums converge or diverge. We already did this for the sum of 1 over n. I used the integral of 1 over x to show that the sum had to diverge. Okay. So just back to that idea, consider the sum as n goes from 1 to infinity of 1 over n. Now that's really a limit of partial sums, remember. Oops, 1 over I. In other words, I have 1 plus 1/2 plus 1/3 all the way up to 1 over n. And I'm looking at the limit of that as n goes to infinity. Compare that to the function f of x equals 1 over x graphically. Say that's the 0.11 right there. I know this function drops down. For example, we have the 0.2 1/2. And we have the 0.3 1/3. So it's supposed to be 1/2 there. And so on. And then in this case, I'm going to look at left-hand endpoints. And these rectangles here are these things I'm adding. Okay, so there's 1, there's 1/2. Next one here is 1/3, and so on down the road. Looking at this right here, I can see the integral from 1 to infinity of my 1 over x dx is smaller than the sum as n goes from 1 to infinity of 1 over n. We know that to do an improper integral like this, I have to rewrite that as the limit as x goes to infinity of the integral from 1 to b of 1 over x dx. What's an antiderivative for 1 over x?
ln x.
ln x, yeah. So this is going to give me the limit as x, as b goes to infinity, b goes to infinity of the natural log of the absolute value of x evaluated from 1 to b. Let's see, so that's going to give me the natural log, natural log of b minus the natural log of 1. What's the natural log of 1?
0.
Yeah, 0. So really all that matters is that right there. And we know that the natural log is asymptotic with the y-axis and then increases forever. So this grows forever. In other words, it does not exist, but in a special way of growing forever. And the integral that I've shown here is always less than the sum. And so for any pair of function versus sequence that I can match up, I can show if one converges, the other converges, or if one diverges, the other diverges. Okay. Now, in this case, to show divergence, I use left-hand endpoints. If I wanted to show convergence, I would use right-hand endpoints. I just shift everything over, and it works the same way. All right, let's try another one. Consider the sum as n goes from 1 to infinity of 1 over n squared. We're going to pair that up with the integral as x goes from 1 to infinity of 1 over x squared. The x, which, thinking about the power rule, we would rather write as x to the negative 2. Technically, I can't plug in infinity, it's a limit, so then we're going to rewrite this as the limit as b goes to infinity, and we're going to have b as an endpoint up there. What's an antiderivative for x to the negative 2?
The negative x to the negative 1.
It is negative x to the negative 1, right? We increase the power, then divide by it. So increasing it to negative 1, divide by negative 1, we get a negative number. So it is negative x to the negative 1, and that's being evaluated from 1 to b here. Now that's really -1 over x. So I have the limit, or -1 over b in this case, as b goes to infinity, of -1 over b minus -1 over, let's see, 1. Which is just going to be a +1 here. And then as b grows, this thing right here is going to 0, right? The numerator's fixed, the denominator's increasing, so that's going to 0. So what is the limit here? The limit is 1. Now, I don't care what number the integral goes to. It could be pi, it could be a million. I don't really care, as long as it exists. That means it converged. So because we found a number here, that means we have a convergent integral. And according to that theorem, the sum must also converge. So here we have convergence by the integral test. Now, just quick graphical check on that right there. This function right here still has the point 1, 1. And then the function just drops down faster than 1 over x did. Now, in this case, I'm trying to show convergence, so I want my sum to be smaller than the integral in general. So to do that, I would just choose left-hand endpoints to make that happen. Now, you may say, well, you got a slight problem there because the integral is starting at 1 and we're missing out on this first term, a sub 1. But when you're adding up a bunch of stuff, it's not the first few terms that matters. It's that infinitely long tail that matters. So this one term is insignificant. What matters is what's going on out here as we head to infinity. And so what we've shown is the rest of these, a2, a3, and so on, they're always underneath a convergent area from this continuous function. This function right here, we found is less than 1. So that means the sum as n goes from 2 to infinity of my function, 1 over n squared, is less than 1, right? Because we have all this extra area that the integral is adding up that the sum is not. Now, I know the first term of my sequence is 1. So if I just add a 1 to both sides, then I know the original sequence I was looking at, n equals 1 to infinity, that sum has to be less than 2. Okay, well, that's kind of cool. I'm narrowing down what its value can be. It's some number less than 2. Can we do better than that? And the answer is yeah. It turns out we can narrow it down even better than that. So we'll look at that next.